sharing my screen. Hopefully you can see the slide and hear me well. So I will give something like 15-20 minutes overview of our SteamDry project. And I'm, like I said, acting as a coordinator for this exercise. I'm here at VTT. I'm a principal scientist, been here quite a long time, mainly acting as a project manager these days. I would like to start with an image. So this is actually taken last summer in a Smurfitvedstrook Parenco mill in the Netherlands. So here you can see actually the most of the presenters today and also the people who have been joining this project and really doing the hard work which is behind the presentations we are going to show today. This SteamDry is an EU project, and it is actually a Horizon program, twin transition, and there is a program called Energy Efficiency Breakthroughs in the Process Industries, and this is actually under that umbrella. It is an IA, so it is an innovation action, meaning that the EU is basically covering the costs. And normally in these innovation actions, we are starting at the technology readiness level of 4, and I hope you are familiar with that scale. And then we are moving higher. So the target is in this project is to reach a technology readiness level of 6, which is a piloting at some relevant scale. And after that, of course, it goes to industrialization, and the 9 in this TRL scale means that it is commercially available. So we are not there yet, but hopefully moving that towards that very fast. We started last year, January 24, and it will continue until summer 27. The total grant for this was almost 10 million euros. And from this map, you can see the partners of this consortium. VTT here in Finland, we are the coordinators. And then we have actually 7 industrial partners. So we have Valmet and Pillar, making this machinery related in this kind of technology. Then we have 5 product manufacturers, Smurfitvedstrook, Sappi, Ahlström, Sofidel, and Metsä Group. And then we have 7 research institutes, and I guess we are all presenting something today. So University of Twente, they are focusing on this steam purification, Wageningen, from this sealing questions, technical challenges there. University of Santiago de Compostela, they are doing this techno-economical assessment, life cycle assessment. Felga from Spain, they are our communication dissemination partner, taking care of that. AIT, the main responsibility of them is to really to simulate these processes and show the potential. BFI is responsible of this modeling, digital twinning, and we are at VTT, we are really coordinating this action, but also involved in many of these work packages, and most importantly on this piloting, and I will come to that a bit later. This superheated steam drying is not exactly a new thing. So there has been an EU project for more than 20 years, and we were actually involved in that. And so some homework has been done, and we know something about that. And so in late 90s, we actually built together with Valmet this kind of a unit. You can see it in this picture. So it was a very slow machine, but it was actually an online web drying machine operating at steam atmosphere. And we really showed in that early work that you can obtain good energy savings numbers, higher than 50%. But because at that time we didn't really know what happens when we put the paper in this kind of a steam dryer. So we were mainly focusing in that study on this quality effects. So what happens to paper when we put it there, and also this drying rate. So how much water can be evaporated with this technology. We already then noticed some technical challenges which were not really solved at that time, because at that time it was all about making paper machines bigger and faster, and really implementing this type of a new technology. It didn't really fit to that world at that time, so I guess we were a bit early with that. Funny thing, you can also see from the image that all these work safety issues were slightly different at that time. So I'm not sure this doesn't really look like any safety boots, or there's no any eye protection or ear protection and things like that. So it's, but luckily these things are a lot better today. When we put a paper in a steam dryer, we are actually using water to dry things. And there is some kind of a fundamental difference, and I'll try to illustrate that with this image. And this is actually a simulation results from Wageningen, and not really verified yet this model since our piloting starts shortly, but just to show what is the big difference between an air dryer and a steam dryer. So here we have a dryer, we have a web going in this kind of a convective hood, then it comes out, enters to the next unit, and then finally comes out. And if the system is working with hot air, what happens that then this orange curve is the steam, the web temperature, it goes up and reaches a wet pulp temperature, and depending on this humidity level of the air, it reaches certain constant level. When it comes out, it cools down in the air before it enters to the next dryer. And when it starts to be almost dry, then it starts to, the temperature starts to rise and close to this air temperature. And then when it is coming out, then it again cools down. And if we do the same thing in steam, so the quite big difference is that the paper is actually in 100 degrees centigrade. In this simulation, the paper is actually so that the other side is on steam, the other side is on paper, which is not really a real case, but just to illustrate the difference. So it very immediately reaches the high temperature, and actually there is some condensation taking place in the early part of the dryer. So the moisture actually goes to the wrong direction. And then it starts to dry, comes out from the dryer, enters the second dryer, and again when getting drier, so then the temperature starts to rise, and then it comes out from the dryer. So the big difference is really this product temperature. In air dryers is somewhere around 50-60 degrees, lower, higher depending on air conditions, and in steam dryer very close to 100 or 100 degrees. And that is why we were a long time ago already expecting some quality changes, and those we are addressing in this project as well. So what we are actually doing in here, so we have set the goal. So we really want to demonstrate this kind of drying technology which radically reduces the energy consumption. And in addition to that, it also reduces the CO2 emissions, since we are not really burning anything to get that dryer medium there. We are electrically heating the steam, and in the next presentations you will hear why that or how that happens. And by doing that, from our proposal, we stated that the energy savings potential is 60%, and during this first year and a half we have been running the project, we have actually seen that it could be a lot higher number than this. In thermal drying, and depending on the machine configuration on the production line, we are somewhere around 40% savings, and totally 100% reduction in CO2 emissions. This project is really focusing on pulp and paper industry, but there are many other industries where this can be applied. So whenever you have this kind of a web-like product, it could be some textile web, non-woven, wood, plies, anything. So basically this technology can be also implemented there. So we have set a set of objectives for us. Like I already mentioned, develop this energy efficient drying technology, achieving a CO2 emission-free process. The process is quite different, obviously, since it is using steam as a drying medium. So we need advanced control systems, and also we are working on those. And big part of this exercise is to pilot something, and I will come to this pilot a bit later, but really show in a real machine that it works, or on a pilot machine that it works. Always when we are thinking and developing new technologies, these environmental and techno-economic assessments are very important. So one work package is really focusing on those, and those can be here. We will hear about those later today. And finally, when having all this, of course, before making any investment decisions, really this business potential has to be there. So that is also one big exercise. And finally, what we are doing today, we are really telling the results. So we are always focusing on this communication, dissemination, that kind of thing. So that's what kind of objectives we have. And if we go a bit deeper to this actual doing, so really we know that there are all kind of dryers out there. And when you like to do something differently, when you want to apply this superheated technology, so what is really the pathway there? So what kind of steps there are, and how this can be applied on the different dryers? That is, that was really probably the main part of the work we have been doing so far. And then these technical challenges I already mentioned. So how we keep this air or the steam free of air. So because when we want to utilize this latent heat which is there, and also using this steam which is coming out from a dryer in some other processes, so we need to be sure that the steam quality is high enough. So there are no any inert gases there, or any solid particles which may harm or be harmful in this machinery. So this is the big technical question, and already mentioned that this controlling of this kind of thing, how we are starting this kind of system, because obviously everything is in air atmosphere in the very beginning, but then when we are now using steam, so how fast this transition happens, what kind of steps are needed there, if something goes wrong, if web breaks, so what needs to be done. So really this advanced control system, digital twinning, that is one work package and big part of this. And once more, piloting. And we have set the target that we would like to show this in a speed of 200 meters per minute. The only system, or the old system I mentioned earlier, was working somewhere around 10-20 meters per minute. So it was really order of magnitude slower than we are doing today. And our pilot where this will be implemented is actually, it can go faster than this, but we have a certain length of a dryer, but we can go beyond this target we set earlier. This is how our project is actually built. I'm not going to spend too much time on these work packages, but always this EU project, you have a certain structure there. We have some management work packages. We have work packages for communication, dissemination, exploitation, IP, and usually we start with all kind of homeworks, really thinking this transition pathway, how this process would look like. We will hear that shortly. And now we are actually working with these technical questions, first in a lab scale and shortly in a pilot scale. And parallel to that, developing these control systems. And when we start to have data from this laboratory and pilot scale studies, then we can really update and start to calculate these LCA technical assessments, how that would look like. And also then we know a lot more about this actual machine solutions, sealing solutions, so then this upscaling strategy can be built. And finally, all this data will be fed to this business case calculations, and that will be a base for this further steps, investment decisions, that kind of things. Okay, and this is actually the one the machine we are going to upgrade. So currently this VTT Sampo pilot line is located here in Jyväskylä, Finland, where I'm sitting. And we currently it is a 700 millimeters wide machine. Here is the forming section, and here are actually the dryers which are currently there. They are operated with hot air, and this hot air, or air is actually heated up by having some kind of burners in the channel. So we are basically burning some natural gas or some gas there, and then impinging those hot air and flue gases on the material to be dried. Or another version is that we can use this true air drying if the material is porous. So these hoods will be replaced by these superheated steam hoods, and also this process, these combustion systems which are out there, we will remove those and place these electrical superheaters there. And this construction is ongoing, and Roope will tell more about this in his presentation. At the same time, we have collected all kind of data from Eurostat, basically calculated or find how many machines there are in Europe making different kind of paper grades, board grades, products, how much energy they are using. So this is something like 400 petajoules energy consumption in drying in Europe today. And then when having this savings potential, we can estimate what would be the savings in our case if this technology is implemented on some percentage of these machines, for example. And similarly, these CO2 emissions from fossil sources, the values are there today, so we can also estimate how much reduction we can gain there. We have also checked where those machines actually are, and since this dryer is actually producing steam, so basically our dryer is like a steam generator after that, so there has to be some usage for that steam. It could be the same machine, some cylinders which are already there, but it could be also some other process. So we went through, and again this is public data, all kind of European industrial sites where they are actually located, and how much emissions they are actually using or producing today. So just to see where this surplus steam could be used either on site or some site which is nearby. And this kind of data set is also collected from public sources, and it contains 2,000 European sites, and if somebody is interested, we can share this data set. When having all that, so we have really then made this kind of a roadmap. So we are now on the piloting stage, or shortly entering there. So we will have a pilot in where we can study this technology, study these technical questions, and see how that really works. And if it works well in this kind of pilot environmental, of course, then the next step would be that, okay, let's do this in full speed. It could be whatever, 1,000 meters per minute or even higher. So there are many machines running a lot faster, 1,500 meters per minute. And Valmet is now our partner in this project, so it could be on their pilot, but it could be also some industrial machine. We don't know that yet. So, and typically this kind of a development takes some years, followed with this lab work which has been there for a long time. But then when having this piloting phase, then a couple of years in let's say some kind of a demonstration, and then finally really entering to industrial markets. But we will hear about those later very shortly. And this roadmap of this SSD superheated steam transition, that is one of our public deliverables. So when you go to this website of this project, you can find the document from there. And finally, if you are interested to follow us, so there's a lot of information which can be found from this www.steamdry.eu, our webpage. We also have a YouTube channel, so there are kind of interviews there, some kind of nice videos, animations there. And from this web page, you can find this kind of infographic, all kind of brochures and more details are actually shown there. And there is a newsletter, so you can put your email address there, and every now and then we are sharing these results in form of newsletter. So if you are interested, please put your name there. And I think that was my last slide. Hopefully you got an idea how this project has been built, what are our targets, and then we will go deeper in these technical details, business potential, all these in the next presentations. Thank you.